So today we'll start to talk about string algorithms, and in the first lecture we'll talk about substring search algorithms. Nice. So what is a string? String is basically an array of letters. So let's say the string is just, let's say, A, B, A, B, B, A, B, and so on. So every string is just a sequence of letters. What you can do with strings, so basic operations, just take any letter of the string. So you can get any letter in constant time, just like an array. So if you have these indices, 0, 1, 2, 5, 6, you may take any letter just by index. Let's say 3 will be B. Some parts of the string have special names. For example, if you take any number of first letters in the string, you will have some prefix of the string. So prefix of the string is like the subarray which contains some first letters, and so it's something from 0 to something like I minus 1. So it will be the prefix of size n. So if you take first I letters of size I, so if you take first I letters of the string, you will have some prefix of the string. In a similar way, you have some last letters of your string. So if you take some last letters of your string, you will have some suffix of the string. Let's see, from I to n minus 1. Every other subarray is called a substring. So if you take substring, if you take some letters from L to R minus 1, you will have some substring of your string. Well, let's talk about some interesting properties of these things. So if you take prefix of any prefix, you will have some prefix. Yeah, obviously. If you take suffix of any suffix, you will have some suffix. If you take some suffix of some prefix, what you will have? You will have some substring. Yeah. So if you have some string, you take some prefix of this string, and then you take some suffix of this prefix. You will have this string. So any substring is a suffix of some prefix. Yeah. And in the same way, so you can think about is every substring as a prefix of some suffix. So you may take this suffix. So your substring will be a prefix of this suffix. So okay. That's just simple definitions of some parts of the string. That's basically all. That's basically all we need in this segment about strings. Nice. So the problem we'll discuss today is a substring search. What is a substring search problem? The problems look like this. You have some big text. Text is simply a large string. Yeah. So we have some large string, and you have some string. Let's say S. And what you need to do is to find this string in this text. So if you consider this text as a string, you need to find some substring of t, which is equal to s. So in this text, we need to find some substring, which is exactly the same as your string. Nice. Okay, that's the whole problem. So we need to find some substring. Let's say for position I, so we need t from I. Let's say the length of this string is n, the length of this string is m. So we need the substring from I to I plus m minus 1 equal to string s. That's the whole problem we'll discuss today. Nice. So let's start with a very simple algorithm. A very simple algorithm will let's do it in a brute force. Let's try to iterate over all possible values of I, and for each position we'll take this string and just compare the string with string s. So we'll iterate over all i's from 0 to n minus m, and then check if string from I to I plus m minus 1 equals to s, then we simply return I. Or if we didn't find anything, let's return something also minus 1. So if we didn't find anything here, we just return minus 1. So like there is no substring equal to s. Yeah. Nice. That's all. It's a very simple algorithm which solves the substring search problem. Let's talk about time complexity of this algorithm. What is time complexity? No, basically this loop makes up to n iterations. So you have n iterations here, but this comparison to strings actually is not in constant time. Yeah, so you can compare to string in constant time. So compared to strings, you need to iterate on all positions, and for each position you need to compare two characters. Yeah, so this comparison of those strings actually works in m time. So total time complexity will be n multiplied by m. Yeah, that's all. So that's the very naive approach to solve this substring search problem. It's pretty slow, but it's correct, right? So what we'll try to do today is to find more clever and more fast way to solve this problem. That's the plan for this lecture. Cool. Cool. So the first approach to improve this time complexity is to use hash functions. So I used to use hashes. What is the idea? Idea is here most of these comparisons are actually false. So if at some point you find some substring equal to s, you immediately return from this loop. So the most time complexity goes from the situations when you compare two strings and actually find out that two strings are not equal. Yeah. So you spend most of your time just declare these two strings are not equal. How can we check that two strings are not equal using hash functions? Instead of comparing these two strings, you can compare the hash functions of these strings. So if you have two strings and they are not equal, then if you calculate any function of these strings, we'll have some hash functions, will be not equal to hash function of b. Yeah? Yeah, now we simply find any occurrence. So we need to find any occurrence of this string in text here. So if we find any string equal to s, we immediately return. That's the first version of this problem. You may have another version of the problem. In some problems, you actually need to find all occurrences of this string. So you need to find all possible positions of I such that this string will be. Yeah, we will consider this problem later. Let's start from this problem. Most of the time here, we will just find out that these strings are not equal. So if these strings are equal, we immediately return. So if we want to optimize the comparison of two strings in case then two strings are not equal. So how we'll optimize it? Instead of comparing these two strings, we will compare the hashes of these two strings. So let's update it a little bit. So what we'll do? Let me just improve it a little bit. So what we'll do? We'll compare the hashes of the strings. If hash of string t from position I to m minus 1 is not equal to hash, let's say it's if it's equal. So if hashes are equal, then we will compare the strings. Like this. So I just added this line to the code. Everything else is the same. And the idea is that usually if two strings are not equal, if we find a good hash function, something good, then most times when we have not equal strings, then the hashes will be not equal. Oh, my bad. Oh, I have implication one way. My bad. Like this. Yeah, my bad. And no one noticed. Huh? So, if two strings are not, if these hashes are not equal, then the strings will not be equal, right? Yeah. Sometimes you may have two different strings having the same hash function. That's a collision, yeah? Sometimes collisions happens. So we need to find a good hash function. We need to find a good hash function such that if two strings are not equal, then the probability. Let's do this also. So if you have two different strings having the same hash, it's called collision. Yeah. We talked about collision last year when we discussed hash tables. Yeah. So it happens. The number of possible values of hash function is less than total number of all strings. So collisions are unavoidable. Yeah. So sometimes you will have a collision with some probability. Yeah. And so that's the first problem. The first problem is that if you have a bad hash function, then you might have multiple number of collisions. So if you choose some bad hash function, then you may have multiple situations when you have equal hash function, but here actually you have different strings. We want to avoid this, so we want the probability of collision be as small as possible. And the second problem is actually that if you want to compare these two hash functions, we actually need to calculate these two hash functions. And calculating hash function of a string takes linear time, yeah? So this calculation of hash functions actually takes linear time. So we didn't improve anything. So if you just take a substring, try to calculate a hash function, you need to iterate over all characters of this string and calculate a hash function. And similar here. Now, here we need to immediately improve it just calculating. We need to calculate hash function of s only once. So we can calculate it only once, somewhere here. So we can calculate it, hash function of s as hash of s, and here just use this value hs. So that's the simple improvement, yeah? So for string s, we need to calculate hash function of the string only once. But here is much more complicated, because here on each iteration of this loop, we need to calculate hash function of some different strings. And yeah, each time it takes a linear time to calculate this hash function. So we need some way to improve this calculation time. So we need to find hash function which can be easily recalculated when you move from one substring to another substring. Got it. So and now we'll solve both these problems. So we'll find some good hash function such that probability of collision is pretty small, and it can be easily recalculated when you shift the position. So if you have hash function of this string, you can easily recalculate the hash function of this string. So when I move from this string to this string, I can recalculate this hash function in constant time. That's the plan. Good. Let's go. We'll use polynomial hash function. Polynomial hash function is a very simple thing. So if you take some string, again, your string contains of some characters, S0, S1, and so on, Sn minus 1. Then the hash of this string will be just some polynomial. Let's say, if you just put numbers instead of characters for each, so each character can be specified as some number, right? So usually you have some fixed number of possible letters in your string. Yeah, so you just enumerate these letters from 0 to something, yeah? So you just use these characters as coefficients of your polynomial. So you have S0 multiplied by x power n minus 1 plus s1 multiplied by x power n minus 2 plus and so on plus sn minus 1 x power 0. Now, if you just consider the polynomial, the value of this polynomial may be pretty large. So here you take x power n minus 1. So if you just calculate this polynomial as integer, the value will be too big. So what we'll do is to take this polynomial modulo m. So we'll take this polynomial modulo m. I believe we discussed it last year when we talked about hash tables, right? So I'll just repeat the same thing. What is x? Good question. Now, like we discussed, yes, we totally discussed it last year. Let's repeat it again. When you choose the hash function, you don't want to choose one hash function. You choose like the set of possible hash functions. So, so this x and m will be the parameters of this hash function. So when you want to choose the hash function, you choose the parameters x and m, and then you have your hash function. So you don't have one hash function, you have like the big set of hash functions, and you choose some random function from this set. So how to choose these values? No, basically m will be chosen as random big prime. How to find a random big prime random we will discuss in the next semester actually. Usually it's not a big problem, so okay. No. So it's not hard to find a big prime number. And x will be just a random number. To m minus 1, I think. Yeah, we totally did it last year. Okay, I'll just repeat the same. Now, I claim that these hash functions will solve both our problems. So it will have the small number of collisions, and it will be easily recalculated here. Why the number of collisions will be small? No, consider two different strings. So if you have two different strings, what is the probability if you have two different strings? What is the probability that the hashes will be the same? Well, let's try to see. So if you have two hashes, so these two hashes are two polynomials. So we need to find, so two polynomials must have the same value. It is the same if the difference of these two polynomials is 0. So if you take the polynomial, let's say a0 minus b0 x power n minus 1 plus a1 minus b1 x power n minus 2 plus and so on plus a n minus 1 minus b n minus 1 x power 0 must be 0. So I just find these two polynomials and take the difference of these two polynomials, right? So this difference is a polynomial of power n. And if you have the value of polynomial equal to 0, it means that x is the root of this polynomial. The root of the polynomial of power n, so for polynomial of power n, there are at most n roots of the polynomial. Their mod should be 0. No, everything mod m, yeah. So I will assume in all future functions, I will assume this modulo n. Okay. I'll assume all later calculations are made modulo m. Okay. Nice. So in all future formulas, I'll just omit this modulo m, just because all formulas will have this modulo m. Everything, everywhere we're working just in modulo m arithmetics. Nice. So x is root of this polynomial. Polynomial of power n has at most n roots. So the number of possible values of x is at most n. And here we pick some random number. So what is the probability that we pick some root of this polynomial? The probability will be no more than n over m, something like that. So just by increasing the value of this m, we can make this probability as small as we need. That's the plan, basically. So the plan is to pick some big random number, big enough so this probability is small. Now we pick some random value of x. If you pick some random value of x, then the probability that you have collision of two strings will be something like that. So it will be small. So probability that we will go here and find out that these two strings are not equal is pretty small. That's all. That's the whole plan. Nice. Okay. Now we'll solve the second problem. Second problem is that we need to be able to recalculate this hash function from this string to this string. So when we know a hash function of these strings, we need to be able to easily recalculate hash function of this string. Again, it can be easily made because these hash functions are polynomials. So we can switch from one polynomial to another polynomial just by making some algebra stuff. Let's go. So let's raise something. What can we raise? Let's raise this. We don't need this anymore. And add this. Let's keep this problem statement for now. Nice. So what's the plan? We know hash function of some substring. So imagine you know the hash function of some substring of t from I minus 1 to, let's say, from I. So you know the hash function of string from I to I plus m minus 1. And when we move from I to I plus 1, we need to, on the next iteration of this loop, we need to find the new hash function, let's say h prime, is the hash function of t from I plus 1 to I plus m. Yeah, like this. Well, let's just write down these two polynomials. So this polynomial is something like this. We take t I, well, let's write something like this, just to keep it consistent. Ti multiplied by x power m minus 1 plus ti plus 1 x m minus 2 plus and so on plus t I plus m minus 1 x power 0. So this is the first polynomial. And the next polynomial will be something like this. We need t I plus 1 x power m minus 1 plus and so on plus t I plus m minus 1 x power 1. I hate this marker. Plus t I plus m x power 0, like this. That's all. That's the first polynomial, that's the second polynomial. And now we need to find a way to construct second polynomial from the first polynomial. To do this, we need to find the similar parts in this polynomial. Let's say, so we need to find the parts which have the same coefficients, right? So let's see. Here we have coefficients from I to I plus m minus 1. Here we have coefficients from I plus 1 to I plus m. So this part is actually similar to this part. So these two parts have the same coefficients. So they only change is the powers of this axis. So to get this part from this part, we just need to take this thing and multiply it by x. So let's do the following thing. So let's take the polynomial h, this polynomial, multiply it by x. Now we need to remove this item. So this item is actually, so we'll multiply it by x, so it will be minus ti x power m. And we need to add this part, so it will be plus ti plus m. That's all. That's how you move from one polynomial to another polynomial. It's clear enough. Looks fine. That's the whole idea of this algorithm. Now let's just write down the algorithm. So the algorithm will work like this. So you calculate the HS again as hash of string S. You calculate the first polynomial with h as hash of t from 0 to n minus 1. And now you iterate for all positions again. N minus m. And just compare these two hashes. So if hashes are the same, then you compare these two strings. T from I to I plus m minus 1 equal to s, then return I. And then you move from this hash to the next hash. So this hash is h, this is h prime. So you just say h equal to, use this formula, h multiplied by x minus ti multiplied by x power m plus ti plus m. Everything modulo m. That's all. If you didn't have anything, just return minus 1. What? Not now. Not now. That's all. That's the whole algorithm. Okay, let's talk about time complexity of the algorithm. So what happens in this algorithm? We sometimes, so this line works in constant time. Yeah, let's see. It's just one. Let's put 1 here. So this line works in constant time. This line works in m. But if strings are actually the same, then you finish. So what will be the total time complexity? So we made n iterations. So we execute this line n times. So let's see. So 1 plus here. If we go here, and these two strings are not equal, then the probability of this will be something like this. So the probability that two strings are not equal is m over n, right? That's the probability that we go here and two strings are not equal. It will multiply it by m. And one last time it will be plus m. So once we need to check that the strings are equal, and because they're actually equal, and then we immediately return. So here this part will be something like 1 plus m squared over m. So if you want if you want the time complexity to be small, you actually need to take the m about m squared at least. So here, when you pick the random big prime number, you need to this number to be as at least m squared, something like this, if you want this algorithm to work smoothly. Nice, that's all. Now, okay, let's discuss some philosophical questions. So I can make this probability as small as possible. So what if I pick a really big prime number here? So if I pick something like 64-bit prime number, or I don't know, 128-bit prime number, so it will fit in int 128. So if this number m is really big, so if, for example, if you pick m like about 2 in power 64, or even about 2 in power 128, then this probability will be actually very small. Yeah. So the probability that different strings have the same hash function will be just so it will be that small. So it will never happen actually. So if you believe your hash function is that good, in some algorithms you can actually believe that if you have two strings with the same hash function, you can just believe that two strings are equal because the probability of the hash collision is that small. That's a tricky situation, because if you make the algorithm which relies on your hash function having no collisions, then you actually make algorithm which sometimes works incorrect. Yeah. So if you just avoid, so what I want to do, I want to just avoid this conversion. I want to compare just two hashes and don't compare these two strings. That's what I want to do. Yeah. Just because if I compare two hashes and they are equal, I just believe that two strings must be equal because the probability of collision is that small. Sometimes you can do it, and actually in real programs, people do it all the time. So in big string algorithms, there are a lot of situations when you can do it like this. Because usually it's because this is the only way to do it. So in some algorithms, there's no way, people don't know any determinant. So people can solve some problems without having tricks like this. So some problems rely on the hash functions having the collisions. If you can avoid this, it's usually better to avoid this because you just made the algorithms which sometimes may fail. And if you make some critical system, you don't want your algorithm to fail. Yeah. If you build in something not that critical, so you build in some, I don't know, something like websites, I don't know. So websites are usually also important. So if you build in some recommendation system, something like that, yeah. So if you once in a year will recommend some wrong song to somebody, it's not a big problem. Yeah, it's bad, but it's not at the end of the world. So if you build in something not that important, it's almost always okay to use something like this. If you just want to optimize the productivity of your system, so if you're making some algorithm which will optimize the workflow in your system, then if you optimize it not very good way, so it's not a big problem. So it will be not that optimal as it could be, but that's not a big deal. So sometimes if your system is not that critical, you can do it without any second thoughts. But sometimes if you make something really critical, you want to kind of avoid situations like this. Okay. Okay, it was some philosophical part of this lecture. Let's move next. Let's talk about it a little bit more. So, actually, this technique is that powerful that not only because you can do a substring search, because if you believe your hash function has no collisions, you may do even more cool stuff. Let's do something even cooler than this. So what you can do with hash functions, you can calculate any hash function of any substring in constant time. Let's do it like this. Consider some string. So you have some string S. It's also not working. Have some string S. I want to be able to calculate the hash function of any substring of this. So I want to calculate, let's see, hash from L to R will be the hash function of substring from L to R minus 1. And I want this function to work in constant time. That's the plan. So I want to be able to calculate any hash function of any substring from L to R in constant time. Now, how can you do it? You can do it after the linear time precalculation. So what you can do? You can precalculate the hash function of all the prefixes of this string and put them into array. So let's say array P contain the hash function of prefix S from 0 to I minus 1. You can precalculate these values in linear time. Is it obvious, or should I write the code? Let's do it. Let's write the code. How to precalculate all these values in linear time? No, it's pretty easy. So you have the hash function of some prefix. Hash function of the prefix is just a polynomial. So you have this polynomial. And you want to build this polynomial. You want to add one more letter to this polynomial. So how to calculate this next polynomial? You just need to take this polynomial, multiply it by x, and then add this last character. So this pi plus 1 will be just the previous polynomial multiplied by x, and add this last element. So this element will be s I, like this. So you can calculate all these hashes in linear time. That's cool. Now, what to do with these values? So if you know the hashes of all the prefixes of your string, you can calculate the hash function of any substring. How to calculate hash function of the substring? So you have this substring. You want to have a polynomial which contains all these coefficients. So let's take the polynomial which corresponds to the right side of this substring. Let's take this polynomial. This polynomial has all the coefficients we need here, but here it has some extra coefficients. So we need to eliminate this part of the polynomial, but this part of the polynomial is basically this hash. So we'll take this big polynomial and subtract this small polynomial multiplied by some x. Yeah? So if you calculate hash function from L to R, you need to take this polynomial for this substring, so it will be PR. And then just subtract this small polynomial PL multiplied by the difference of the powers. Yeah? So these coefficients have different powers of x. So just to normalize them, you need to multiply this polynomial by the x power the difference of lengths of this polynomial. So the x power R minus L. That's all. And now just by using this formula, you can calculate the hash of any substring. That's kind of cool, because when you can calculate the hash of any substring, you can compare two substrings. You can take any two substrings of your string and compare them. Are they equal or not? And that's quite powerful, actually. Nice. Nice. One final part. Sometimes you want to do something like that. You want to compare, for example, you have some set of strings and you want to find the number of different strings in your set. So what you can do is to put all your strings in the set and then find the size of the set, yeah? But if strings are large, then you don't want to do this. Instead, you can just put the hashes of the string in the set. So if you put k strings in the set and then check the size of the set. So if you have some set of strings, yes, S1, S2, and so on, Sk, and then you calculate the hashes of this string and put them in the set. So let's make the set of hashes of Si. Yeah. So let's calculate hash from every string and put all these hashes into set. What will be the probability that you have no problems here? Again, let's say the probability of single collision is P. Then what's the probability that you have at least one collision in this set? Again, in this set, you have k-square pairs of strings. And every pair in this set may have a collision. So the probability of at least one collision in the set will be about, not exactly, but if probability is small, it's good enough. So it's about k square multiplied by p. So you need to be here. You need to be careful. Here, since you have k square here, it grows pretty fast. So if you have even if you have some 1,000 string in your set, the probability will be multiplied by 1,000,000. If you have 1,000,000 string in your set, probability will be multiplied by some trillion. Yeah. So the probability grows here pretty fast. So you need to be careful here. Again, if your probability is really small, like if you have 1 to 28-bit prime number, so it's usually not a big problem. But even if you have 64-bit prime number, here you may have some problems. So you need to be careful here. Just a small remark about this. Nice. Now let's move some algorithms. So this algorithm is pretty powerful. All this technique about hash functions is a very powerful technique. But it uses some magic, so we use some randomness, so sometimes it works, sometimes it's not. This time complexity is not real-time complexity, it's like expected time complexity and so on. So we will now we'll move to other algorithms which has no random functions and no magic, just standard algorithms. So the first general algorithm we'll discuss is the Knuth-Morris-Pratt algorithm. One of the most classical algorithms about strings. Knuth-Morris-Pratt algorithm. Yes, I believe Knuth actually co-invented this algorithm. Yeah. It's the same Knuth, which, yes, yeah. Let's go. So what is Knuth-Morris-Pratt algorithm? Knuth-Morris-Pratt is very simple, actually, very simple linear algorithm which can be used to find the substring. The core idea of this algorithm is to use some prefix function. Why should multiply? I already erased it. Sorry. Let's move on. You can rewatch the lecture later, okay? So what is a prefix function? Prefix function is very simple thing. Let's call the prefix, let's call pref of s is the largest string which is both prefix and suffix of s. And suffix of s, and not equal to s. So for the string we need to find the largest string which is not equal to the whole string s, but which is the prefix of the string and also the suffix of the string s. Just draw some pictures. So we have the string s. We need to find some substring which is here and also here. Yep. So this will be the pref of s. Sorry. Okay, no, let's try. So for example, pref, let's say, of something like a, b, b, a, b. So if you take string like this, the largest string which is both prefix and suffix is ab. So we have ab here and ab here. So the prefix function will be ab. Great. Let's say, for example, prefix function of ab, ab, a. What will be the prefix function of this string? Okay, I have like 30 seconds delay, so I will just make some pause. ABA, nice. So this prefix and suffix makes an overlap. So we have this ABA and this ABA. They are overlapping, but that's okay. We allow these two strings to overlap. Now, for example, prefix of say something like ABB. So for these two strings, there are no string which is both prefix and suffix. So prefix function will be an empty string. And let's see, finally, the prefix function of an empty string just 5 seconds. Oh, Twitch is that fast. It's cool. So the prefix function of an empty string will be not defined. Why it's not defined? Because we want to find substring which is both prefix and suffix but not equal to s. So empty string is equal to s. So we don't want the prefix function of string will be the string itself. So prefix function for empty string is just not defined. Nice. That's all we need to know about prefix function. Okay. Now the next exercise. Imagine you have some string. And I want to find all possible strings which are both prefix and suffix of s. Imagine you can calculate this prefix function. What is I want? So I want to find all strings, which are both prefix and suffix of x. So prefix function just gives you the largest such string. So what if we need to find all possible prefixes and suffixes of this x? How can we find all such strings? No, you can do it like this. Let's try to iterate all such strings by decreasing the length of the string. So first let's find the largest string which is both prefix and suffix. It will be just the prefix function of s. So just take the largest string here, So this string is just a pref of s. So it's not working. So this is the largest string which is both prefix and suffix of s. So now let's find the next string. So the next string here must be equal to this. So how to find the next string which is both prefix and suffix of s? Well, it's easy to see just by this picture. So this next string must be a prefix of this prefix of s, and also must be a suffix of this string. Yes, so this orange string is the prefix of this violet, I believe, string, and is also the suffix of this violet string. I'm not sure if you can read the colors, but fine. So this function is both prefix and suffix of this violet string. So it will be the prefix function of the prefix function of s. Not this. And so on. If you want to find the next string, again, it will be the prefix of this one and suffix of this one. So it will be prefix of pref of pref of s, and so on. So you just continue to apply this prefix function of pref of s. Yep. You just continue to apply this prefix function. You will find all the strings which are both prefix and suffix of s. Nice. That's all. That's how we do it. Cool. Now let's move to the algorithm. So what is the Knuth-Morris-Pratt algorithm? Knuth-Morris-Pratt algorithm is basically building the prefix function for all prefixes of string s. So I given the string s, and we will calculate the following array. Let's just save some space here. So what I want to do, I want to calculate the prefix function for all prefixes of string s. So I given the string s, and I want to calculate the array p of I will be the prefix function of the prefix of size I. Let's say it's from 0 to I minus 1. That's what basically Knuth-Morris algorithm does. Right? So given some string, and you want to calculate this array of prefix functions. First of all, I don't want to have this array as array of strings. Yeah? Well, since array of strings has to use too much memory. Yeah? So instead of having this array as array of strings, I only need to have a length of this string. Right? No, let's see here. So I want to calculate prefix function of some prefix. So prefix function of some prefix will be another prefix of s. Since prefix of prefix is prefix. So this prefix function will always be some prefix of string s. So to define some prefix, you just need to find the length of this prefix. So instead of having this prefix function as strings, I will have only array of integers. So I will have the length of this prefix actually. For example, let's build some string. Let's have some string. Let's say again a b, b a, b b a b, and so on. Something like that. Now, what will array p look like? Let's have some indices here. So we have indices 0, 1, 5, 6, 7, 8, 9. So what will be p of 0? P of 0 is the prefix function of an empty string. Prefix function of an empty string is not defined. So we'll put here minus 1. It turns out that minus 1 is a good value. Just for implementation reasons. Now here, p of 1 is prefix function of string of 1 character. It will be an empty string. So p of 1 will be 0. Now, prefix function of ab is also an empty string, so it will be also 0. abb is also 0. Now here we go. Here, the string abba. So the largest string, which is both prefix and suffix of this abba, is a. So a is the largest possible string, which is both prefix and suffix of abba. So prefix function of this prefix of length 4 is 1. Here the same thing, so the largest string which is prefix and suffix is 1. Here it is 2, since we have string AB. Yeah? So for this prefix, we have string AB here and AB here. So its length is 2. Here the length is 3. Here again we have A, and here we have A. So the length will be 4. And finally here the largest string will have size 2, right? Since we have string AB and string AB here. Again, that's the whole thing. So now we will build the algorithm which makes this array from this string in linear time. That's the whole plan. So how the KMP algorithm works? We just go from left to right and calculate these values from left to right. So we'll just go from left to right, and each time we take some position and calculate this value using some previous calculated values. So how to calculate the next value of P? Well, let's say again, So let's have this string S, and we want to calculate value of Pi. So value of Pi is the prefix function of string of first I characters. So it's first, this is I. So I want to calculate the prefix function for this prefix. Prefix function of some prefix is just some string. So I need to find this string equal to this string. So when I want to calculate value Pi, I want to calculate the prefix function for this prefix. Prefix function of this prefix is some string which is both here and here. So I need to find the length of this part which is the same here and here. Now, let's take this last character. So let's take this last character here. If we just remove this character from this string, so let's take everything except this X. Let's take this part. It will be the same here and here. And this character X should be the same here and here. Like this. So your prefix function contains two parts. You contain this blue string plus character X. Now, this blue string is actually a prefix and suffix of this prefix of size I-1. So what we need to do? We need to find some string which is both prefix and suffix of this prefix of size I-1. And we need to add this character X to the end of this. So we need to find such string which is same here and here. And also we need to check that this character X is equal to this character X here. Clear enough? That's the plan. So how to find such strings? We will iterate all substrings which are both prefix and suffix of this prefix of size I-1. Just iterate for all of them until we find substring which have character X here. And when we find some string which has character X here, we'll find the largest possible string which is the prefix and suffix of this prefix. That's the whole plan. So yeah, we will iterate all the substrings using this technique. So I will start by taking the prefix function of this prefix of size I-1. Then I will take prefix function of prefix function and so on. So I will iterate all such strings until I find this character X. We just stop saying that everything is clear, so I continue to say the same thing over and over again. Go here. So again, what's the plan? Let's take this prefix of size I-1. Let's take the prefix function of this prefix. It is already calculated, so let's find the largest string, which is same here and here. If we have character X here, then we can use this string as a prefix function of prefix I-1. If character X is here, then we have this string equal to this string. If we have some different character here, so if we have character Y here, then these two strings are different. So we need to find some smaller string. So let's take the prefix function of this prefix function and find the next string. So we find the next string here. So this string will be pref of I minus 1. This string will be pref of pref. Let's p. Let's just use p. So this will have p of I minus 1. This will be p of I minus 1. Yeah. Let's take the next string and check this character. If this character is x, then we can use this string s, because it is the same here. If here we have some character z, so again, these two characters are different. Let's take prefix function of this prefix function of this prefix function and use small string until we find character x here. So if we have character x here, then you can use this string because these two strings will be the same. That's the whole plan. Nice. Let's write the code. Code is really simple. So we will we'll say this array p. Let's say p of minus 1 is of 0. P of 0 is minus 1. Then we iterate over all values from 0 to n. From 1 to n. We have the value of 0. Yeah? Now let's take the length of the string as some variable k. So first say k is pi minus 1. And now we just iterate through all these strings until we find this character. So while k is non-m, while it didn't finish either. So when we move from characters, so in the last iteration of this loop, we actually will move from 0 to minus 1 and we will end this loop. So if while k is not 0 and string in position k, so k is the length of the string. So this indices are from 0 to k minus 1. So this character index k is not equal to s I minus 1. We just continue to the next prefix, like this. We'll talk about time complexity. It actually has linear time complexity. We'll discuss it in a moment. So we continue to the next string. And when we stop, then we either have the k equal to minus 1, or we have some string so that we can add the next character to this string. In both cases, p of I should be equal to k plus 1. That's why we put minus 1 here. So we don't have extra if here. Again, we end this loop in two situations. When we find some string which have character x here, so we add this character x here. So the length of this string is k. So if we add this character x to this string, the length of this string will be k plus 1. And if we just if we try all these substrings and none of them works, then the result must be 0, since we cannot add this x to any substring like here. So the result must be 0. But we will end with k equal to minus 1. So we add 1 to this minus 1, and we'll have 0. Just a small trick. Nice. That's all. That's the whole KMP algorithm. Very simple algorithm. Just 5 lines of code. You can actually, I believe you can optimize it to like 3 lines of code, but that's all. Now, let's talk about time complexity. I claim the time complexity of this algorithm is linear. Let's prove this. Why the time complexity is linear? Well, let's check. So, everything here is linear except this while. So, everything except this while is actually linear, quite obviously, right? So, what we need to prove is that the total number of iterations of this loop is linear. How to prove the total number of iterations of this loop is linear? Let's look at the variable k. Let's look at variable k. What happens to this variable k? In this while loop, the value of variable k is always decreasing. So in this while loop, k is always decreasing. On each iteration, we've moved to some value to some smaller value. So p of k is always strictly smaller than k. Now, what happens to variable loop when we move from one iteration to another iteration? So when we move from here to here. So let's see what we do here. We put value k plus 1 to position I, then we increase I and take from the same cell of this array the value of k. So simply we take some element of the array, put k minus 1 here, and then take from the same element a value k. Yeah? So basically, from when you move from here to here, the k will be increased by 1. So here you make k plus plus actually. So the value of variable k is increased by 1 in every iteration of this loop, but in every iteration of this while loop, it is decreasing. So you increase the value of k at most n times, and you decrease this value in every iteration of this loop. So you cannot decrease the value more than n times, since you increased it only by n here. So the total number of decreasing of this variable k is at most n. That's all. That's why it's linear. No, another way to think about it is just to look at this length of this. So k is basically the length of this string. So what happens to this string? So every time you have some string. So in the previous iteration you had this string. Yeah? So the length of the string is basically k. So what you do in this algorithm, you try to decrease this string until you find. So you in this while loop you decrease this string until you find some string which has the same character here, and then you add this one extra character to the string. So basically, if you look at the left border of this string, it's like two pointers method, yeah, like in merge search, something like that. So every time in this while loop, we move the left border of this string to the right. And we cannot move this left border to the right more than n times. So the total number of iterations of this while loop is actually linear. Again, it's the same like in two pointers method. Nice. So this one is linear. So again, we built some linear algorithm which constructs this array P from string S. Now, how to use this algorithm to find, actually, we forgot about the problem we're solving. We tried to solve the problem of substring search. So how to apply this algorithm to find the substrings? The easiest way to do it, again, we have this text, and we have a string. Let's make it smaller. So we have a text and we have a string, and we need to find some substring here equals to S. So how to do it using KMP algorithm? The easiest way to do it is just like this. Let's construct one big string from these two strings. So let's construct a following string. Let's take string S, then add some special character here, and add the text here. So let's construct this string. Let's construct the long string using this S and T, and just split into some special character which is not occurred in this both strings. Did you take a look? What look? Huh? Did I miss something? Sorry. Now let's build this long string, and then build the prefix function for this string. So what happens if you have So if you have string S here, so if you have here a substring equal to S, then for this prefix, you will have prefix function. So for this I, you will have prefix function of I, P of I. We call it P, equal to length of string S. So if you need to find a substring, you can construct this string, then apply KMP algorithm, build array P, and then look at position when the size of this prefix function equals to the length of S. So if the size prefix function equal to length of S, then you have this string equal to string S. That's all. Oh. Okay, I believe that's all. That's the Knuth-Morris-Pratt algorithm. Okay, it's very simple. It's very fast. It works in linear time with very small constant factor actually. So it's a very usable algorithm, not only for substring search, but for multiple other cases. So we'll discuss some other usages of this algorithm in various problems in the practice next week, maybe next week, maybe in 2 weeks. We'll see. Nice. So I want to discuss one more algorithm. Do we have time for this? I believe we do. So let's discuss one more algorithm, which is also useful and also works on linear time. It's slightly different, but it's also quite important for some substring algorithms. So let's talk about that algorithm. Let's just keep it for a second. We'll discuss suffix arrays. Yes, we'll discuss suffix arrays in later lectures. Yeah, we'll discuss both suffix arrays and suffix trees in this course. Yeah, yeah. What? Yes, you actually. We'll discuss it. Let's discuss it in the home task. You can build a finite state automata from this function actually. Yes, you can think about this function p as a function for your finite state automaton. You can do it. Let's discuss it in lectures. It's actually quite cool. You can use it as a states of finite state automaton and then use this automaton to apply some dynamic programming or stuff. So yeah, we will do it. Go. Yeah, let's talk about that algorithm. So what is the Z algorithm? Z algorithm, very actually strange name for the algorithm, but it's naming here is really strange, but you're given some string again. So given some string S. What you want to do is calculate array Z, which is kind of the same as array P, but slightly different. So what we'll have in position I. So what you want to do, you want to take the position I in your string, and then find the longest string, which is the same here and here. So you want to start in position I and find the longest prefix of string S from this position. Let's say it will be maximal k, such that string from 0 to k minus 1 is the same as string from I to I plus k minus 1. Something like this. It looks kind of the same like prefix function, yes? So, but you calculate prefix function in the end of the string, so you will calculate the same value here, right? So when you're standing here, you will find this string when you calculate prefix function. But in that algorithm, you want to calculate this value when you're standing in the left side of the string. So it's kind of the same thing, but looking from the left, but not from the right. So it uses different technique to calculate. Oh. It's live lectures. So it's I love live lectures. That just because you don't have to just tell about algorithms. We just having a conversation, right? You can drink tea when you're writing an online course, but you can do it in live lectures. That's cool. What I was talking about? Oh, so that's the problem. We have the string and we need to calculate these values, and we want to calculate these values in linear time again. Go. So let's start with very simple algorithm. So how to calculate its values slowly? Well, let's do it like this. So we'll iterate over all values. Yes, z of 0 is kind of strange thing. So z of 0 is a strange value. We will not use it, z of 0. So that if you start from I equal to 0, it kind of just by definition it should be equal to n, but it's kind of strange to have the z function of 0. So we will never use z of 0. So we'll start from 1 here. For I from 1 to m minus 1, let's say n minus 1. We don't have text, so let's use n minus 1. So let's go from left to right and try to calculate these values. How to calculate this value? Again, let's say, let's do it like this. Let's say zi equal to 0, and we'll just increment it by 1. So, while we have the same character here and here, we'll just increment the value. Yeah. As simple as that. So this is just the naive approach to calculate the z array for the given string. But it is slow, yes. Again, this is a quadratic algorithm, so this while may work slowly. You may have, for example, if the whole string contains the same characters, then each time you have the same character, so you just go from 0 to the maximal value, so total time complexity will be n squared. Yeah. And now we will just apply a small trick, very small trick. What I will try to do is to initialize this value. So I want to skip some characters which I already know to be equal. How to do it? Draw a big picture. So I have this string s. I have this position I here. I have this position I. Let's remember, so I already calculate all the values from 1 to I minus 1. So for all these positions, I already calculated the value of the z. Yeah. So what I will remember? I will remember from all these positions the largest block going to the largest position to the right. So from all the calculated positions, I will remember one position which have this string as far to the right as possible. It's actually even 2. So I want this string to be equal to this string. And from all these positions, I will remember the rightmost one. So I want this z, this l. So I want remember l such that l plus z at l is as max as possible. From all positions from 1 to I minus 1. So this is L, so this position is L plus Z of L, right? So it's easy to maintain this variable, right? So you just calculate for all positions this sum and take the maximal value of this sum. So it's nothing interesting here. But what's interesting here? Let's see. Let's look at this position I. So this part of the string is actually equal to this part of the string. And what I want to do in this algorithm, I want to compare the string, the characters from position I to the right, to the prefix of the string. So I want to compare these characters to the prefix of the string. But if I have these characters equal to this prefix, then I also have these characters equal to prefix. So again, these characters are same as these characters, and these characters are same as these characters. And this position is actually I minus L. So what I want to do, I want to check the position I minus L, check the Z function in this position, and just use all these characters, just to skip all these characters when I calculate this initial value. So how many characters can I skip? I want to skip at most Z of I minus L characters. At most Z of I minus L. And also I want to skip at most the size of this red thing, because when I reach the end of this blue string, I have the different characters. So all these characters equal to these characters, and these characters equal to these characters. So I cannot skip more than these many characters. So I want to skip at most L plus Z L minus I characters. So this is the maximum number of characters I can safely skip. So again, this number of characters are the same characters here and here. And these many characters are the same in this position and in the prefix. So if these characters are the same here, and also the same here and in the prefix, then they are the same here and in the prefix. So this number of characters can be safely skipped. Yes? Actually, not like this. You need to take. You actually need to also do it like this. I always forgot about this. That's actually important. Because sometimes you can have a negative value here, but it's just small implementation details. No, this value can be negative. So if you just apply this, I will have negative value of that. You don't want to have negative values of that. That's all. So again, what we do? We skip all the characters we know were equal. Now we just apply this operation like before, and in the end we update the value of L. Let's say if I plus Zi is more than L plus ZL, then just update L. Yes, you also need to do some trick to find this first value of Z. There are different ways to do it. So when you calculate the first value of Z, Z of 1, yes, you don't have the previous values, so L is undefined, so some tricks. No, you can do it. You can do it as an exercise. Okay, so the first value of Z must be calculated slightly differently, because you don't have all the previous values. You can't apply this. You can do it various ways. Okay, you can do it. It's not that important. So nice. That's the whole Z algorithm. Now let's talk about time complexity. Again, I claim that time complexity of this algorithm is linear. Why it is linear? Again, like before, everything except this while loop works in linear time. So we only need to think about total number of iterations in these whiles. So everything else is linear, so we only need to consider this while loop. Now, what happens in this while loop? I claim, so again, let's see. Why first? Let's think why we actually can go in this while loop. So what happens if we go in this left loop? If this green string is actually shorter than this red string, then we have some character x here and some characters x here. And when we calculated this value I minus L, we actually stopped here. So this character is not equal to this character. So here we have x and here we have y. Again, if this green string is shorter than this red string, then we have the same character here and different characters here and here. So when we calculated this z function, we stopped at this character. So we will stop at this character as well. So if green string is shorter than the red string, we will not make any iteration in this while loop. Yeah. So we'll just check the first character and immediately skip it. So we only make this while loop when this green string comes to this position. So the only way we can do it is when you have something like this. When you have blue string to this position and blue string to this position. Okay. So you may only have iterations of this while loop when you reach the end here. Oh, oh, oh. So the characters here are different. So here are x and here are y. Here's y. This is L plus ZL. And these two characters are the same. This is the only way how can you get any iterations in this while loop. So again, these two characters must be the same. So these two characters must be different. So you start from here. That's all. And what happens if you have any iteration in this while loop? So if you make iteration in this while loop, it means that you extend your Z block to the right from this position. So your Z block will be from here to here. So every time in this while loop, you actually move the right border of your current block. So every time you move this, you increase this value of zi, you move the right border of your block. But since you extend this right border of the current block, your block will have the larger sum than z block of L. So if you make at least one iteration here, it means that if you make at least one iteration, then your value zi plus I will be more than the value zl plus L. Okay. But it does mean that you will update the value of L here. So you will update the value of L here. So your sum zi plus I will be the next sum zl plus L. And you increase this sum in every iteration of this loop. So in every iteration of this loop, you actually increase the value zl plus L. That's all. The value zl plus L should be no more than 2n. So you can't make more than 2n iterations of this loop. That's all. So total time complexity is linear. Again, the proof. If you make at least one iteration of this loop, it means that your character here is the same as the character here, but in position I minus L, you had two different characters. It means that you reach the right end of this blue block. Yeah? If you reach the right end of this blue block, then your sum zi plus zi will be more than sum L plus ZL. So you will update the value L here. And also in every iteration of this loop, you increase the value zi. So the total sum L plus ZL will be increased in each iteration of this loop. This sum should be no more than 2n. So actually no more than n. So you make no more than n iterations of this while loop. That's all. Yeah, but basically you move this right boundary of the string to the right. And you cannot do it more than n times. Again, it's like two pointers method, but from different side. And again, how to use the Z algorithm to find the substring? You can do it. You can do the same thing. You just take the string S, make sharp, string t. And again, in this string you calculate this z algorithm. You run that algorithm, calculate the function. So if you have the same string here and here, then in this position you will have z of I equal to m. That's all. Just another way to think about substrings. Okay, this both algorithm KMP and Z algorithm do kind of the same thing, but from different sides. And so sometimes for some problems it's easier to think about prefix function. For some problems it's easier to think about Z function. It depends on just the statement of your problem. So sometimes you use this, sometimes you use that. These two arrays can be actually easily transformed from one to other. So if you have array P from KMP algorithm, you can build array Z from that algorithm, and vice versa. If you have this array Z, you can build array P, and so on. So it's kind of the same array, just we view it from different sides. We'll do it in practice next week. Okay. Fine. That's all for today.